So in this example, we're going to solve an exponential equation by finding a common base. Now, in some cases, when you're solving exponential equations, and we have exponential equations or exponential expressions on both sides of the equation, we may be able to solve it by writing both sides as the same base. So this is just one strategy that we can use. In this case, we can do that because we can write 1/2 as 2 to the negative first, and we can write 4 as 2 squared. Both sides we can write as the same number to a power. So we can rewrite it as 2 to the negative first, raised to the x plus 7th, equals 2 squared, raised to the 3x. Next thing, we apply exponent properties here. When you have a power to a power, you multiply the exponents. So 2 to the power multiply -1 times x plus 7. And on the other one, multiply 2 times 3x, so 2 to the power of 6x. Now that we have this, since exponential functions are one-to-one, we have a property that allows us to cancel out the logarithms and just focus on the exponents, because if the, I said cancel out logarithms, cancel out the exponentials, because if the bases are the same, then the exponents also have to be the same as well, since they are one-to-one. Another way of looking at it is just taking log base 2 on both sides here and canceling out the bases. So we have -1 times x plus 7 equals 6x. And then from there, it's either a linear or quadratic equation, depending on the particular problem. So we have -1x minus 7 equals 6x. I'll add 1x to both sides. -7 equals 7x, and divide by 7. So x equals -1. So in this example, we're going to be solving the equation 2 to the power of x plus 3 minus 1 equals 19. So in order to do that, you'll notice that x only occurs one time. Since x occurs one time, we're just going to do this with reverse order of operations. Get rid of anything outside our key feature, then get rid of that key feature, then finish solving. So the key feature in this problem is the exponential, which is this part right there. So we'll get rid of anything that's not a part of the number in its power. So we'll add 1 to both sides. Give us 2 to the x plus 3 equals 20. Now we have to cancel out the base. So to cancel out 2 to the power, we'll use log base 2 on both sides. Log base 2 and 2 to the power cancels out, leaving me with x plus 3 equals. Now log base 2 of 20, log base 2 of 20 isn't actually a whole number. It's going to be a decimal here. Most calculators, you would have to use the change of base formula or look through a crazy long menu to find it. But we would be doing ln of 20 divided by ln of 2 is how we can type it into the calculator, making sure we open and close parentheses where necessary, depending on the calculator. So ln 20 divided by ln 2 in my fancy calculator. I totally didn't even type in half the numbers I needed to do. 20 divided by ln 2. Oh my gosh. There we go. Kept typing over it. So we have 4.322 if I round to 3 decimal places. Then I have one more step to get x by itself. I'll subtract 3 from both sides. Get x equals 1.322 as an approximate answer. Since we did have to round, you can also keep it as an exact answer. Most people will accept it. The exact answer would be, well, at this point here, we can't actually evaluate the log base 20 or log base 2 of 20 without going into decimals and rounding. So we would just leave it like that and then subtract 3, tagging the 3 on to the end of the logarithm. Since it doesn't actually affect the 20, since the 20 is inside, well, the 3 is done after the logarithm appears, so it's going to be outside the logarithm. So in this one, this is similar to one of the earlier examples where we have an exponential on both sides of the equation. However, what's different is we can't nicely write both exponentials as the same base to a power, like we did earlier with the 1/2 and the 4. There is kind of a way to do it, but it's not a pretty way of doing it. So what we're going to do instead is we're just simply going to solve it by taking the log on both sides. Now we could either do log base 3 or log base 5. Or we could do ln or log. Since we're going to have to use a calculator in the long run, I'm going to choose ln. The most common ones for this particular problem will be ln or log base 10, because those are both on most handout calculators. I prefer ln because it's slightly less writing. Now, unlike normal, ln and 3 to the power don't cancel out, so it's going to stay ln of 3 to the power of x plus 1 equals same thing on the other side, ln of 5 to the power of x. So what was the purpose of doing that if nothing canceled out? Well, this allows us to use logarithm properties to simplify both sides, which is a very common strategy in some types of problems. It's used very often in calculus to simplify some more complex equations. Maybe not often. I might be over-exaggerating with often. But according to logarithm properties, we can move an exponent down in front as a coefficient. Same thing on the other side. On this left side, we're going to distribute just like normal. You can picture what we have right now as something like this. It's very similar to, say, something like this. I probably shouldn't have used the same numbers. Remember that log base 3 or ln of 3 and ln of 5 are just numbers. They're not the prettiest numbers, but they are just numbers. They're representing a number. So it's a very similar situation to what I wrote out here. It just looks a little bit more complicated because of the ln's. But we'll distribute it through. So we'll have x, ln of 3. We can't actually multiply them. And then ln of 3 times 1 would be 1 ln of 3. But that can get confusing, so I'm not even going to put the 1 there. I erased a little too much. So we just have 1 ln of 3 or ln of 3. On the other side, we have x ln of 5. Now our next move needs to be getting all the x's to one side of the equation and getting all the terms without an x to the other side. Since it looks to be easier to move this term to the other side, that looks to be the most effective way to get all the x's to one side. That's what I'm going to do. So I'm going to subtract x ln of 3 from both sides. So those will cancel, leaving me the ln of 3 equals. Now a lot of people try to actually subtract the numbers, but you can't do that because those two numbers are inside the logarithm. So logarithm must happen first, and as far as order of operations go, you can consider it at the degree of exponents. So please excuse my dear Aunt Sally. So exponents would have to happen before addition and subtraction happens. So we can't add and subtract the numbers there. These are not like terms. Just because they both have x and ln doesn't make them like terms where we can add or subtract the numbers. These are not coefficients. They are part of the logarithms. So it must stay x ln of 5 minus x ln of 3, or you can write it in a different order, but it has to be something to that effect. The next approach, or next strategy we're going to look at is just pulling out an x from both terms. That's going to leave us with ln of 3 equals x times ln of 5 minus ln of 3. Now let me reiterate before finishing this. This is the same thing as something like this. It's the same exact thing. It may not look like it, but it is. We have a number on one side of the equation. ln of 3, remember, is a number. And we have x times another number. So x times another number. Our number here, the ln of 5 minus ln of 3, that is a number. Ln of 5 is some decimal. Ln of 3 is some other decimal, like 1 point something for both of them. But a number minus a number is still a number. This is just not a pretty representation of our number. And in order to get x by itself over here, in that basic situation, we would divide both sides by 2, divide both sides by our number that's connected to x by multiplication. So we will do the same thing here. Divide both sides by ln of 5 minus ln of 3. So we'll have as an answer x equals ln of 3 over ln of 5 minus ln of 3 as an exact answer. You may also write it in a couple other forms, or I can think of one other form right now. So we could also write it as ln of 3 over ln of 5/3. It doesn't really change much writing it like that. Or you can get it as a decimal approximation by typing in the following. Depending on how your calculator works, remember this might be slightly different. We need an extra set of parentheses, so we'd have ln of 5 minus ln of 3 on the bottom. And that's how we would end up typing it into the calculator. See if I can get my calculator to be cooperative. Ln of 3 divided by ln of 5 minus ln of 3. So I got 2.151 if I round to 3 decimal places. So that's the approximate answer, and the exact is over there on the right. Two different versions for the exact. Okay, in this example, we're going to be solving the equation 2 log base 3 of 5 equals log base 3 of 2x minus, log base 3 of, in parentheses, 2x minus 3. Now, this equation has two separate logarithms in it. A general approach to having two separate logarithms, or an equation with two separate logarithms in it, is one of two things. One thing would be to get one logarithm on each side. The other is to get logarithms on one side and anything outside on the other side of the equation, depending on the situation, which one you want to go with. Since this one just has two logarithms, we don't really have any other terms connected on the outside of the logarithm by addition and subtraction. The best approach is probably just to have one log on each side. So we don't quite have one log on each side because we do have this 2 out in front of the first log. So we'll have to deal with that first. We'll apply exponent properties to move it up as an exponent. I said exponent properties. Logarithm properties to move it up as an exponent, making it log base 3 of 5 squared. But 5 squared is 25, so we have log base 3 of 25 equals log base 3 of 2x minus 3. And just like exponentials, logarithms are one-to-one functions. So we can apply equality property of logarithms to cancel out the logs or ignore the logs. Or you can look at it like this, making both sides an exponent of 3, which cancels out the logarithms. Either way you look at it, we have 25 equals 2x minus 3. And from there, it's just a two-step equation. Plus 3 to get 28 equals 2x, 2x, and then divide both sides by 2, x equals 14. Now we do need to check a lot of the logarithm equations for extraneous solutions here. So we're going to check them by just plugging the answers back into the original. Now what we're checking isn't necessarily that both sides come out to be the same like we often would. In this case, we want to make sure that our answer, or our possible answer, does not violate the domain of a logarithm, which means that whatever this simplifies to be inside the logarithm has to be positive, has to be greater than 0, it cannot be 0, or negative. So on the left side, we just have the 5, so that's good. We're check out there, because it was 5 in the first place. On the right side, we have 2 times 14, which is 28, and 28 minus 3 is 25. So log base 3 of 25. Now that we've verified that the domain is valid, we have concluded that there are no extraneous solutions here. However, if you want to be sure that these two sides are equivalent, because we haven't completely checked our answers to make sure we didn't make any algebraic mistakes, but if you want to check them completely, just finish either rewriting one or both sides or typing both sides into a calculator. But I can easily rewrite this into log base 3 of 5 squared. And according to logarithm properties, we can move it down into the front, which gives us the other side. But again, my main goal was check for extraneous, which means we just have to make sure there's no domain issues with negative numbers or 0 inside the logarithm. Okay, here we have an additional equation with logs on each side. This one, however, we don't have to use logarithm properties to start it out because there's nothing outside the logarithms. So we can just go ahead and get rid of the logarithms either by using the equality property, or the fact that it's 1 to 1, or making both sides an exponent of e to cancel out the natural log. So we'll have x squared minus 16 equals 6x. Now this equation here is a quadratic, so I'm going to get all my terms to one side since I have both x squared and x. So I'll subtract 6x from both sides. It's going to have x squared minus 6x minus 16, writing it in standard form to make it easier to deal with factoring. I'll go through and factor it next, multiplying first and last. Negative 16x squared. The combination of factors that adds up to be the middle term are going to be positive 2 and negative 8. Since we do not have a leading coefficient, we don't have to do all the factoring by grouping steps, and we'll jump straight to the factors of x plus 2 and x minus 8. And if x plus 2 and x minus 8 are our factors, then the roots are x equals negative 2 and x equals positive 8. Now, with logarithm equations, you do want to double check answers. Sometimes you get extraneous solutions. Extraneous solutions come from the domain of the original expressions. So what we're going to do is we're going to go back up to the original equation and just plug in our two x values. So ln, we'll start with negative 2, so negative 2 squared minus 16. Is that equal to ln of 6 times negative 2? We're not so much concerned that they are equal, we're really majorly concerned that it doesn't make the inside of a logarithm negative. Like on the right here, 6 times negative 2 is negative 12. Can't have a negative inside the radical. It's a big no-no. So even if they do come out to be the same on both sides, it doesn't matter because there's a negative underneath the radical, and we can't have that. Checking the 8, so ln of 8 squared minus 16 equals ln of 6 times 8. 8 squared is 64. 64 minus 16 is 48. So ln of 48 equals 6 times 8 is also 48. So ln of 48 equals ln of 48. We are good. And I was really checking extraneous solutions, so I was more concerned with the fact that this number on the inside was not negative. That was my major concern. Okay, in this example, we're going to be solving this equation, log of, in parentheses, 2x plus 1 to the 5th power equals x minus 2. Now, since we have just a single logarithm, one of the general strategies, and we used this strategy before whenever it was radicals, is move anything outside the logarithm, or in the time we used it before, radical, to the other side, which is already done for us, and then just get rid of that key feature. So to cancel out log base 10, we use 10 to the power. But we actually run into a problem here. It doesn't actually work as nicely as it does with radicals. I mean, whenever it's radicals, if we still have a radical afterwards, we just do it again and again until we get rid of the radical. Eventually you will. Might just have a couple extraneous solutions. But here we have an issue. This time we have an exponential. If we go through that same mindset to get rid of the exponential, we would do log base 10 on both sides. But that kind of puts us back where we start. And as it turns out, there is no algebraic strategy to actually solve this, at least to my knowledge. And I've looked for this for quite a bit, trying to find a way to solve it algebraically. What makes it hard or impossible to solve algebraically is the fact that there's the x inside the logarithm and the x outside. And the same goes for an exponential if you have an x inside and an x outside the exponential. Of course, there are rare cases where you might be able to solve algebraically, but those would be special cases. And in general, there is no algebraic solving strategy. So, as far as how can we actually get the answer to this equation, well, there are three major strategies when solving equations. The first is what you spend most of your time learning in algebra, the algebraic strategy. The second strategy is ways we've usually used to check our answers, or if it's a multiple choice question, it's a good strategy as well, guess and check. Of course, there's other names for guess and check, like plug and chug, and a bunch of other general terms. But it just comes down to just try and answer. If it doesn't work, adjust until you get closer and closer and closer. And the third way that we have looked at is graphically. Now, most of the time graphically is done whenever you're doing systems, but we've also done it with regular equations as well, and I encourage people to use it as a way of checking your answers. So for this, graphically is the best option we have, because we already mentioned algebraically, there is no known strategy, at least to my knowledge, that you can solve this equation with algebraically. Guess and check, well, we could guess and check this, but who knows what this could be. It could be some crazy small decimal that we would spend hours trying to guess. So yeah, guess and check is not efficient. We could do it, but again, not efficient. So let's go graphically. Graphically will get us there. So if I try graphically here, let's try to zoom in the right direction here. There we go. So when you do graphically, solve equations by graphically, whether it's Desmos or handheld graphing calculator, you're going to graph each side as its own equation. So we have y equals, this is log, so functions log, where's log? Log, and now I have 2x plus 1 to the 5th power, but I'm not 100% sure how this is going to interpret it when I put the the exponent if I put it on the outside of the automatic parentheses for the log. So I'm just going to give myself an extra set of parentheses just to be safe. 2x plus 1, I forgot the x. Close parentheses to the 5th power, and then I'll have the closing parentheses for the log. So there's my first equation typed in. My second equation would be y equals x minus 2. Okay, so we have that done. Now, when you solve equations, the solutions, if you have more than one thing graphed, the solutions are represented by their intersections. So you can see we have two intersections, one here and one there. Specifically intersections of the two lines we graphed, not with the x and y axis. So those are the 2 points. However, our original equation only has a single variable. And the variable that matches when we typed it into the calculator is x. And in most cases, it will be x. Because our original equation was a single variable equation, we're only going to use the x values as the solutions. So the two solutions are x equals 8.204 and x equals 0 or negative 0.329. And there we have it. Whew.